Hey guys, so two videos in one day. That's exciting. I just got back from a bike ride today, and I was a bit disappointed for two reasons. One is I had to cut it short because it rained, and the second reason is I just got my emails from tries I had registered for. All three of them are canceled because of stupid COVID. Anyway, so today we're going to look a bit more at Bronsted-Lowry acids and bases, and we're going to be looking at how to calculate out pH of weak acids again. But also, how would you solve a question where you knew maybe the pH of the weak acid, and you were asked to find maybe the Ka of the acid you're looking for? Maybe it's not on the data table, or you're being asked to find the initial concentration. So we're going to look at a few questions like that today. So let's go back to our Google Classroom, and then we're going to go to our OneNote here. Okay, so that was the last video. You might remember that question. And what I look at now is a different question here, but dealing with the same concept. So I'm going to flip my computer over here. Hopefully this will work nicely. And let's say questions. Just think of a question that would be we could pose here. So let's say you're told that you have a solution of, let's just pick a good acid here, of, how about, what's a cool looking name one? Hydrocyanic acid. Cyanic acid. So that's a non-oxy acid. Hydrocyanic acid with a pH equal to, let's say 5.26. Okay, so 2 sig fig number there. And what you're going to be asked is determine the initial concentration of the acid. So sometimes the question will just say determine the concentration. Determine the concentration of the acid. Okay, so we got to be careful with this because there's several concentrations we'll be able to determine from this. We want to make sure we calculate out the correct one. So when we talk about the concentration of the acid, we're saying its initial concentration before it ionized. So we might remember the question above. I'm going to go way up here to the very first question we did here. And this is the one with the 0.1 molar HCl solution. So I'm just going to draw a little arrow or a little mark around this. And so we said that if the concentration of the acid was 0.010 molar, that the pH would have been 2 and 2.00. And we made I made a point of stressing that technically there is no HCl in that container. It's completely ionized into hydrogen ions or hydronium and chloride, and all the acid has been ionized. But technically the bottle, if you were picking up a bottle in a lab, it would have read 0.010 molar. And that would be assumed to be how many moles of HCl you had per liter. And then it ionizes, of course, after that. So when we go down to this question, and we just posed here, what we're looking at is before the hydrocyanic acid ionizes, what was its concentration? So similar to the HCl, was it 0.01 or 0.0001, or maybe it was 2 molar or something? So the first thing I would get you guys to do is to write out the equilibrium reaction. So hydrocyanic acid is HCN. So once again, feel free to pause the video and try to work ahead if you can. Even if you can, if you have to watch the whole video to see how it's done, what I would encourage you to do is redo the question again afterwards and see if you can do it on your own. Without looking at the notes, and that'll sort of show you whether or not you can actually do it. Sometimes what'll happen is you'll do a couple steps and you're like, oh, what was that last step? That means you didn't know how to do it. So you have to go back and maybe revisit the pattern here. So anyway, so that's just my advice for you. So we're going to react that with water, and we know that it should produce an equilibrium of cyanide ions and hydronium. And we know that there would have been an initial amount, and then it would have shifted. A change and an equilibrium. So I'm going to do another ice table question here. And what I would do right off the bat is write my Ka expression, which is a cyanide ion multiplied by hydronium, all over the concentration of the HCN. And I know from the data table, HCN is 4.9 multiplied by 10 to the minus 10. I'm just going to double check that again. Yeah, there we go. So that's a really small Ka value. So we're talking very low ionization here for this. So this question is basically the reverse of the questions you were doing in the last video. And what I mean by that is you're already told the pH of the solution. So you technically, you know, or you could at least figure out the concentration of the hydrogen ion in that solution. But what I'm going to say is initially there would have been 0 cyanide and there would have been 0 hydronium. And then, of course, the concentration of the HCN would have been a certain number, and that's actually what we're trying to find out. So I'm going to make that X. And I don't care about the water because it's a liquid here. So I know the reaction is going to shift to the right. So that side's going to go up, right side goes up, left side goes down. Okay, so now obviously I'm trying to get this X here. I'm trying to find out what that X is. So I got to get some numbers here, otherwise I'm going to be out of luck on this. And so I'm going to use the pH number of 5.26. So I know that I can determine hydrogen ion concentration by taking the antilog of the pH. So that would be 10 to the negative 5.26. And if I use my calculator, that gives me a number of negative 5.26, gives me a number of 5.495, and it's a bunch of other numbers, times 10 to the negative 6. Now, I could use that number on my calculator, but it's going to basically, I mean, I do a lot of writing of lots of numbers. So I'm going to put down this number here, the antilog number. So at equilibrium, the concentration should be 10 to the negative 5.26. And I'm not too worried about leaving it like that because that's not really my final answer. That's just a number I'm going to work with as I go through the calculation. So right now, that's all I know. That's all I've been told in the question. But from that, I can determine a lot of other things that are quite useful for me here. So one is that I started with 0 and I wound up with that number, which means the change had to be that number. So 10 to the negative 5.26. And of course, this is a 1-to-1 ratio. So every time you make 1 hydronium, you make 1 cyanide. So this would be also 10 to the negative 5.26. So down here would be 10 to the negative 5.26. And over here, we'd be minusing 10 to the negative 5.26. So down here, we would have X minus 10 to the negative 5.26. Okay, so now I have a Ka expression that I worked out earlier. Just a bunch of concentrations multiplied and divided by each other, and they're supposed to equal 4.9 times 10 to the minus 10. So I'm going to take my E row, my equilibrium row, and plug those numbers in. So once again, I'm going to plug in this 10 to the negative 5.26. I'm going to keep it like that because I'm going to use my calculator anyway to solve the question. And then I have to square that because I'm timesing those two numbers together. It's Cn minus times H3O plus. And then that's all going to be over top of X minus 10 to the negative 5.26. And that should equal 4.9 times 10 to the minus 10. Now you might remember from the other video, we wrote an assumption statement next here. And that was done because we wanted to not deal with a quadratic equation. It was easier for us to, well, sorry, you haven't used the quadratic formula. It's still a quadratic equation. But this equation is not quadratic. Although we're squaring the top number, there's no variable in there. So really the only variable we have is in the bottom, which is this x. And that's being raised to the first power. So that's a linear math problem. So I'm going to not use the assumption rule here. And the reason is I don't need to. I don't need to use it. In fact, if you do use the assumption rule, then what you're actually going to find out is the concentration of the HCN at equilibrium. And not what its original concentration was. And if it's a small ionization, you might get away with that and you won't notice a difference. But maybe on the test, I won't allow that to happen. I might actually choose a question where there is a difference going on. And you can use just simple algebra to solve this. So here I'm going to cross multiply. So I'm going to say, let's use a different color here. So I'm going to say x. Actually, let's do it this way. Let's show us a couple steps here. So we're going to say 10 to the negative 5.26 squared. And I'm going to divide that by the Ka, 4.9 times 10 to the minus 10. And that's going to equal x minus 10 to the negative 5.26. So I'm kind of cross multiplying. I'm taking this number here, I'm putting it under there, I'm dividing both sides by that, and I'm taking that number and bringing it up to that side. So to isolate the x, I would bring this amount over. So I would say this is x equals 10 to the negative 5.26 all squared. And I'm going to use a calculator to work that out anyway. 4.9 times 10 to the minus 10. And then I'm going to add 10 to the negative 5.26 to that. So let's work that out. So hopefully I'm going to get this right. So 10 raised to the negative 5.26, and then I need to square that number, and then divide it by the Ka of 4.9 times 10 to the negative 10. And that's pretty small, but not as small as adding this number. Adding 10 raised to the negative 5.26. So that's going to give us an x value equal to 0.061637 and change. Now, so what is x? Well, x is, going back to the table, x is the concentration of the HCN at equilibrium, or sorry, at initial state, so before it ionizes. So that actually is our answer. So HCN, let's see, over here, HCN is equal to, and I guess I'm going to need 2 sig figs here, 0.062 molar. Okay, now I'm going to work this out and see if this actually gives me, my screen's doing something weird here. I'm going to plug this into the equation. I'm just trying to undo something. I'm going to pause the video here just because something's not working for me. Okay, so I think I got it working. There we go. Okay, so that would be our concentration of our acid. Now I'm going to do a quick check here. I'm going to plug these numbers in and see if this works. So if, what is going on? Oh, there we go. Oh my goodness. There we go. Let's close that down. Okay, I think that should work now. Okay, so let's work that, see if we get our right Ka value. So I'm going to go 10 raised to the negative 5.26, and then I got to square that number, and now I'm going to divide it by my x value, which is 0.061637 minus 10 raised to the negative 5.26, close bracket. And I'm getting 4.9 times 10 to the minus 10. So I could plug it back in to see if it works from here. So that concentration is fairly low. But the big thing I want you to notice here is that we didn't use the assumption rule. So, so if you're not getting a quadratic equation, you do not use the assumption rule. Otherwise, you're solving for the equilibrium concentration. And of course, it would depend on the change here. If the change is quite large, as you would get, not so much for HCN, but if I was working with, say, iodic acid or oxalic acid, which is higher up on the table, that change is not going to be negligible. It's going to make a difference. You're going to see a difference between the I amount and the E amount. So the assumption rule is only used when we use the quadratic equation. And that's usually when you're told the concentration of this and you're trying to find out the other number, the hydronium. Okay, so let's try another question kind of like that. And I'm going to try a base question, see what you guys think about this one. So let's take, let's say NH3, ammonia, okay? Take ammonia. And let's say you have 0.50 molar ammonia. Sorry, that's kind of poorly written. So let's say a 0.50 molar ammonia. And the question is, determine the pH. And we'll say and pOH too. Let's say pH and pOH. We'll find both numbers here, okay? So the first thing I have to do is write out some kind of equilibrium reaction because I know that that chemical is weak. If you go in the data table, once again, take a look for ammonia, and you should see that it does appear on both sides of the data table, but it can only act as a base, and also it only acts as a weak base. So it actually takes a proton from the water, making ammonium ion, and also hydroxides. So it is going to make hydroxide, which means it's going to make it basic. So you're going to get more hydroxide than hydronium. So it's going to be a basic compound. And once again, I would do an ice table here. I'd set up an ice table. And I would say the initial concentration is 0.50, no water, 0, 0. And now it's going to shift. Okay, so basically that's all I kind of know right now. So I'm going to switch colors for things I don't know. So it's going to go up here, has to shift to the right, and it's going to decrease on this side. And why not, let's say we're trying to find pH and pOH, so why don't we find the hydroxide concentration, because we would have to know that to determine either of those. And of course, if we go from 0 to x, we have to be increasing by x on both. So x down here, and we must be decreasing by x here. Okay, so now I'm going to write my K statement. Now I got to be careful. That doesn't start with a K, but we have to be careful because this is a base. So I'm not going to be working out Ka. I'm going to be working out Kb. Okay, and the Kb would be the concentration of the products, NH4 plus, multiplied by the hydroxides, all over the concentration of the base, NH3. Now I need to be really careful because the data table does not tell us the Kb value. It only tells us Ka. So to get the Kb, we do Kw divide by the Ka of the conjugate acid to, this is NH3, right? So we're looking at NH3. So the conjugate acid of NH3 is NH4 plus, which really is this compound. That's its conjugate acid. So if I look that up on the data table, going down the acid column for NH4 plus, or you could actually go down the base column for NH3, and what you'll find is the Ka value is 5.6 multiplied by 10 to the minus 10. Boy, we seem to be sticking with this minus 10 number a lot. So 5.6 times 10 to the minus 10, just double checking. Yep, looks good. Okay, so now I'm going to plug my numbers in. I'm going to say x times x is x squared all over 0.50 minus x equaling, now it should equal that number, but I'm going to be using my calculator down the road, so I'm just going to leave it like that fraction. So I'm going to go little ditto marks here, okay? Because I think what would be good here is just to do as one big calculation as opposed to multiple steps. Now I'm going to think here for a second. If I was to cross multiply, I'm going to create one of these quadratics. So do you think we should use the assumption rule or not? Well, we should use the assumption rule because we don't want to deal with the quadratic formula. So I'm going to assume that the amount of ionization is very low and that this number is pretty much equal to 0.5. But I think we would all agree it can't be 0.5. It's got to be a little bit less because some of it did ionize. But let's use our assumption rule here. So we're going to say x squared all over 0.50 is equal to this number. Okay, so what I'm going to do is I'm going to cross multiply. So now I'm going to write out the numbers again. So 1.00 times 10 to the minus 14. And I'm going to divide that by the Ka of NH4 plus, which is 5.6 times 10 to the minus 10. And then I'm going to square root both sides of the equation to get x. So I just do this as a single calculation, so I'm not trying to carry numbers and maybe I round a number the wrong way and stuff like that. So I just do it as one big calculation. Oh, actually, I did forget one thing here. Sorry, I was talking too much. I need to times this by 0.5. I cross multiply. So you cross multiply and then you square root. I left that out. Okay, so let's do that. Okay, so 1 times 10 to the minus 14 times that by 0.5, the concentration of the acid. And then I'm going to divide that by 5.6 times 10 to the minus 10. And I get that number, and then I can just square root that number. So I square root it. And I get 2.9887, bunch of other numbers. I'm not rounding yet, times 10 to the minus 3. Okay, so I'm just going to double check that again. So let's go, so that number, let's plug that in. So let's square that number and divide it by 0.5. And then I'm going to times it by 5.6 exponent minus 10. There we go. Looks nice. Okay, now we want to be careful here about negative logging this number and what it's going to tell us here. So we were actually asked to find the pH, but then I said you could also find the pOH. So what we have to realize is what this X stands for. So going back to the equation, or the equilibrium table here, X is the concentration of hydroxide. So this X value is your concentration of hydroxide ions that are in solution. So really it's that molarity of hydroxide. So if I want to find pH or pOH, I think it'd be better to find pOH first, like just take the negative log of this number. And so I'm going to take the negative log of this number, okay? And that's going to give me, let's see here, negative log. We're going to negative log of 2.98807 times 10 to the minus 3. And that gives us a number of 2.52. I believe that's right. 2.52, but now you might think, well, that's really acidic. That's quite acidic. It's a low number, isn't it? But you're not finding the pH right now. You're finding the pOH. So that's the pOH measurement of this compound. So the pH measurement would equal 14 minus the pOH. So that's going to be 14 minus that number, and we get 11.46. 48, sorry, 48. Okay, so that's actually quite basic. It's quite high up there on the basic side of things. So ammonia is at this concentration would be quite basic here. So I hope that makes sense for working out the pH of a weak base here. So I'm going to do one more question, and I think we'll call it quits here and give you some stuff to kind of work on for this. I'm just going to turn to this section. Just hang in there a sec for me. Yeah, okay, let's do. Okay, here, let's try this here, okay? So let's say you have a compound, and I'm going to give you a compound you haven't seen before, okay? So let's call it example here. We'll give it a fancy name here. Let's give it a fancy name. Let's call it Bardia, okay? Bardia. How about Bardia? Because Bardia is a person in our class. How we go Bardias? Okay, there we go. So Bardia, so not the same thing. So very different. So Bardias is a special chemical, and it has a pH. So a solution of Bardias has a pH equal to, let's say, 11.333. Okay. So, and we're going to say that the concentration of this chemical, so we're going to say the initial concentration, so the initial concentration of Bardias is equal to 0.400 molar. Okay, and we're going to say, we're ask you determine the Kb value for Bardias. Okay, so there's our sort of our setup of our question, and it's a bit different than the other ones we've been looking at here. So I think the first thing we should do is write some kind of equilibrium statement here, and so you have to sort of read carefully what you're being told, because you're going to have to determine, is Bardias, is it an acid or a base? What kind of compound is this? Well, there's sort of two giveaways in the question. One is the actual question itself, but the other is the pH number. You have a pH of 11.333. So that's definitely basic. So whatever chemical this is, it has to produce hydroxide ions. It must take protons from water here. So what I'm going to do is make a symbol up for Bardia's, and I'm not going to use the whole word because it's a lot to write. So I'm just going to write B, and I'm just going to give it a minus charge here. But you could write whatever you want. I just think it's easier to write a single variable for it here. And I'm going to say it's reacting with water. Now it's acting as a base, so it's going to take a proton to form HB and also some hydroxide ions. Okay. Now we have an initial concentration, we have a change, and we have a new equilibrium. Okay. Oopsie, I'm going to draw my line down here. Let's get rid of that weird line there. Okay, and I'm going to write a K expression, and once again I have to determine what kind of K I'm going to write here. This is going to be a KB. Okay, KB for this. Okay, so what could I do? Well, I could say this is equal to the concentration of HB times the hydroxide concentration all over the concentration of B minus, this Bardia's stuff. Okay, now I'm being asked to find the KB value, so that seems pretty clear. I'm going to need to have some numbers here to do this. And basically, I think as long as I can get these three numbers here, I should just plug them into the calculator and I'm off to the races. Okay, but I got to be careful how I interpret this. Okay, so I'm told that the initial concentration is 0.4. So I'm going to use green for what I know already. Okay, so I know this is 0.400. That's the initial concentration, and I know this would be 0 and 0. Okay, because it hasn't ionized yet. But when it does ionize, I get a pH equal to 11.333. So how could we use that number to figure out something useful here? Okay, because I don't even see anything here that deals with hydronium. What I'm trying to find out, I guess, is hydroxide. That would be useful. So why not convert this pH to a pOH measurement? So this would be 14 minus the pH measurement. So the pOH would be 14. Let's get this on my calculator. So it'd be 14 minus 11.333. And that gives me a pOH measurement of 2.667. Okay. So from that, I can find the hydroxide concentration, because it would be the antilog of the pOH. So 10 to the negative 2.667. Okay. So I know this number is 10 to the negative 2.667. And just like the last question, I'm going to leave it like that for now, because it's just a number I'm going to use to calculate out things here. So far in green, that's what I know. I know that those numbers. What am I trying to find out here? Well, I guess I should try to find out what the change is. And I know that this must have gone up by the same number. This must have gone up by the same number. And it must have gone down by the same number. And I know this here would be 10 to the negative 2.667. And over here would be 0.400 minus 10 to the negative 2.667. Okay, so what am I trying to figure out? Well, I'm trying to find out the KB value, which means I need three numbers to plug in there. Which row of the table do you use? Which row of the table would you use to plug these numbers in? Like, would you use the I row? Would you use the C row? Would you use the E row? Well, the K value is an equilibrium value. So it's the numbers of the chemicals at equilibrium. So you should be using the E row. So I think the row we want to use is our equilibrium row. So I'm going to plug those numbers into the calculator here. So, or into the formula first and then the calculator. So basically the number on top is the same. So I'll say 10 to the negative 2.667 all squared divided by 0.400 minus 10 to the negative 2.667. And I'm going to put this in brackets because my calculator will give me the wrong answer if I don't do it that way. Well, sorry, unless I do it that way. So let's work that out. So let's see what our K value is for this. Where are we here? There we go. My calculator. Okay, so I have 10 raised to the negative 2.667, and then I need to square that number. And then I'm going to divide that by bracket 0.4 minus 10 raised to the negative 2.667, and then close that bracket. And that would equal 1.1, and sig figs here are 3 sig figs, I believe. 1.165 times 10. Oh no, actually 1. Not a pH measurement. 1.17 multiplied by 10 to the minus 5. Okay, so the Kb value, as you know, is not huge, but definitely not super small. So this is definitely a weak acid here. Okay, so I'm going to stop the video here and give you a few more questions to work on. And then we're going to be talking about our last big unit in this chapter. So our next test could be as early as next week sometime. So I'm thinking maybe Wednesday or Thursday of next week. So anyway, but I'll definitely post that on the Google Classroom for you. So have a good night. I know I will. And just stop the video. So have a good night, guys.